In this video, we're concerned with conditional probability. That is to say, we'll ask about the probability of some event, say F, given that some other event, say E, has occurred. We use this piece of notation to express the conditional probability of F given that E has occurred, and we compute it as the probability of the intersection of F and E divided by the probability of E. Our formula suggests that when calculating the probability of F given E, we effectively shrink the sample space to include only those outcomes consistent with the occurrence of E. Then figure out what fraction of the shrunken space still involves outcomes from F. Let's diagram that out. Here's the sample space omega for the experiment represented as a rectangle. Here's the event E, and here's the event F. And here's their intersection. It contains all outcomes that are part of both events. Since we're given that E has occurred, we can shrink the sample space by discarding all outcomes not found in E. Once we do that, our picture looks like this. As the remaining picture suggests, the probability that we observe something in F is now simply the area of this shaded region, expressed as a fraction of the total remaining area. It's this observation that leads to the formula you see on the left. Let's try an example. We'll roll two fair dice yet again, but now we'll ask, what's the probability the dice sum to 6 if they land on different numbers? So here we've got F as the event the numbers showing sum to 6. We have E as the event the numbers showing are different, and we're looking to compute the probability of F given E. It helps if we lay out all 36 equally likely outcomes of the experiment. As before, the columns of this table are labeled with the possible numbers that show on the first die, while the rows are labeled with the possible numbers showing on the second die. We'll fill in the table by adding the sum of the numbers showing on the dice. Remember, these are equally likely outcomes. The event F corresponds to this subset of the sample space, while the event E corresponds to the disjoint subset I've traced out here. Our formula asks us to find the probability of the intersection of events. I'll highlight that intersection here. It contains 4 of the 36 equally likely outcomes. So, P F intersect E is equal to 4 over 36. To get P of E, we note that the equally likely outcomes in here and in here total 30. So the probability of E is 30 out of 36. Putting it all together, we find that the probability of F given E is 2 over 15. Connected to our discussion of conditional probability is the notion of independence. Two events E and F are independent if the probability of their intersection is equal to the product of their individual probabilities. If E and F are independent, then the occurrence of E has no bearing on the likelihood of F. Using our calculating formula, in this case, we can see that the probability of F given E boils down to the probability of F alone. Independence is nice because it makes it easy to calculate the probability of seemingly complicated events. Suppose, for example, we toss a fair coin twice in succession and want to know the probability of observing heads both times. Okay, not the most complicated of events, but it can illustrate the point. We model the two tosses as independent events, and so the probability that we see heads the first time and heads again the second time is the probability of heads in a given trial multiplied by itself. Since heads is one of two equally likely outcomes for any given coin toss, the probability of its occurrence is 1 over 2. So our answer is 1/2 squared, or 1/4. I'd like to discuss another way in which conditional probability helps express our uncertainty. To do this, I'll need a bit of jargon. We'll say that a mutually exclusive and exhaustive collection of events is a group of events, say E1 to En, possessing two basic properties. First, in order to qualify as mutually exclusive and exhaustive, the union of all events in the group, E1 to En, must be equal to omega. That is to say, the events in the group must fill, or exhaust, the entire sample space. Second, the intersection of distinct pairs of events in the group must be the empty set. In other words, distinct pairs of events in the group must be mutually exclusive. Let's look at this definition with a picture. Here's the entire sample space represented as a rectangle, and here are three events. These events are mutually exclusive and exhaustive because they fill the entire rectangle, but don't overlap one another. Now, it turns out that any event, say F, can be partitioned into a number of disjoint pieces based on areas of overlap with members of the mutually exclusive and exhaustive set. This ultimately means that calculation of the probability of F can be expressed as the sum of the probabilities of F intersected with each member of the mutually exclusive and exhaustive set, like shown here. As an aside, note that we can rearrange our formula for conditional probability to express the probability of the intersection of two events like this. Building on this insight, we can say that after it has been decomposed, the probability of F can be written using conditional probabilities as follows. What we've just discovered is called the law of total probability. It says that if E1 to En is a mutually exclusive and exhaustive set of events, then the probability of F can be expressed as a weighted sum of conditional probabilities, as shown here. The weights in the sum are the probabilities of the various members of the mutually exclusive and exhaustive set, again, as shown here. As a special case, note that an event E and its complement EC form a mutually exclusive and exhaustive set. Thus, according to the law of total probability, the probability of F can be written as follows. Using the fact that the probability of EC is 1 minus the probability of E, we can simplify this decomposition and express the probability of F like this. This says that the probability of F is equal to the probability of F given that E has occurred times the probability of E plus the probability of F given that E did not occur times 1 minus the probability of E. It turns out we've already unknowingly applied the law of total probability in a previous video. The application came during our discussion of sex determination in bees. At the time, the probability argument was a bit of a black box. Given that we're more experienced mathematicians now, the probability argument we used deserves a second look. I'll remind you that sex determination in bees is connected to ploidy. Females develop from fertilized eggs and are diploid as a result. Females inherit a copy of each gene from both mom and dad. Males, on the other hand, develop from unfertilized eggs, are haploid, and inherit only one copy of each gene from mom. We were, and still are, interested in the event that an allele in the current population descended from one carried by a male exactly t generations ago. So let's define m sub t as this event. Our goal here is to devise a recursive model for the probability of m sub t. We'll do that using the law of total probability. Consider the event m sub t minus 1. This is the event that the allele we've chosen from the current population descended from a male exactly t minus 1 generations ago. Events m sub t minus 1 and its complement form a mutually exclusive and exhaustive set. The line of descent to the allele in the present-day population must have passed through either a male or a female T-1 generations ago, and if it passed through a male T-1 generations ago, it could not have passed through a female, and vice versa. It follows from the law of total probability that P of m sub t can be decomposed as follows. As an aside, let's calculate the conditional probabilities that appear in this equation, starting with this one. The probability that the allele was carried by a male T generations ago, given it was carried by a male T-1 generations ago. I'll make a little picture here to help us out. We're working on the assumption that T-1 generations ago, the ancestor of the gene was found in a male, and so it must have descended from a female in the previous generation. Remember, time flows in this direction, and we're looking back into the past. Based on the picture, we can say that the probability the allele descended from a male T generations ago, in this case, is 0. Shifting gears, we'll now work on the assumption that the ancestral allele was found in a female T-1 generations ago. In other words, the line of descent passed through one of two alleles that were equally likely to have come from a male or female in the previous generation. It follows that the conditional probability in this case is 1/2. Returning to the main formula and subbing in our results, we arrive here. Using the fact that the probability of the complement of m sub t-1 is simply 1 minus p of m sub t-1, we end up with the recursive model we were looking for. This recursive equation is, in fact, the same one we developed in an earlier video. However, in that video we had used different notation. We used a p sub t where we now use a probability of m sub t. If we furnish this recursion with an initial condition, then it can be solved using approaches we've already encountered. However, we're satisfied since we've sorted the probability argument here. Here's a recap of what we've done in this video. We defined conditional probability, in other words, the probability of f given E, and we saw an example of how to compute it. In that example, we rolled a pair of fair dice. We also defined what it means for events to be independent of one another, and we investigated yet another example. That second example involved flipping a fair coin and was meant to show how independence makes our probability calculations easier. Finally, we discovered the law of total probability, and we used it to develop more carefully a recursive model we had seen in a previous lesson. That recursive model related to sex determination in bees. After you've come to terms with the ideas introduced in this video, you should be able to do several things. First and foremost, you should be able to compute conditional probabilities using the formula we derived. It's also reasonable to expect you'd be able to manipulate the formula to say things about its other elements. Next, you should be able to explain what it means for events to be independent, use details of that explanation to show that given events are or are not independent of one another, and use the notion of independence itself to compute the probability of the intersection of events. Finally, you'll be able to state the law of total probability and use it in your probability calculations going forward. I know I'm running the risk of sounding like a broken record, but I'll say it anyway. Watching this video can't be the only thing you do to master this course. Do the readings, try the problems, and discuss ideas with your classmates. Mixing it up like this is a good way to set yourself up for long-term success in mathematics, so don't be afraid to give it a try. So I feel like when I say omega, it sounds like